Hello, my name is Khai, and this is part 4 of my project. Today I will be going over the chemistry involved in pesticides. First, I will be talking about organophosphorus. Organophosphorus is another class of pesticide that is often an alternative to using organochlorines. This is because some are more effective and healthier than organochlorines, but as time went on, they have become as unhealthy, if not worse, than organochlorines. Another advantage of organophosphorus is that they don't persist in the environment as much as organochlorines. That at least still remains true. Organophosphorus are similar to organochlorines in the sense that instead of being hydrocarbons with at least one covalently bonded chlorine, they are hydrocarbons with at least one covalently bonded phosphorus. They require at least one organic molecule. Sorry, I was talking and my microphone cut out. What I was saying is that they require at least one organic molecule or atom, and it is not required to be carbon. Their primary use is in pest control, and they have a reputation for being highly effective insecticides. Organophosphorus are also extremely versatile in their oxidation state as they are in their properties. Some organophosphorus are used as flame retardants, but for the purpose of my project, I will narrow it down to only the organophosphorus used in pesticides. There are two organophosphorus used in pesticides. The two types are phosphonic acids and phosphinic acids. These two categories are also extremely versatile within themselves. A type of phosphonate is used in a drug to treat osteoporosis, and its close brother gives others cancer. To add on to that, these two types of organophosphorus are also in something called sarin. Sarin is a nerve agent that is violent and extremely toxic chemical warfare weapon. All that to exemplify the versatility and uniqueness of organophosphorus and specifically phosphonic and phosphinic acids. A reminder that everything I just mentioned is the same material that is used in the pesticides. And moving on to the next presentation will be focused on the physical models used when measuring and understanding pesticides. The first physical model I would like to go over is the UV spectrophotometer. Sorry if I'm pronouncing that a little awkwardly. The UV spectrophotometer. It helps measure the amount of pesticides in agricultural products, and obviously it has a wide variety of uses besides just this. It does this by measuring the light intensity of a light source that has been across a visible wavelength range. This light source has been a sample of what is trying to be measured. This light source has a sample of what is trying to be measured, and after the experiment is finished, the light absorbed, transmitted, or reflected is measured to determine the amount of pesticides and chemicals present in agricultural products. I'm sorry if this is a little bit confusing because it is kind of difficult to explain. And the next two tools used for pesticides are gas chromatography and high-performance liquid chromatography. Gas chromatography serves a similar purpose to the UV spectrophotometer. It separates the chemical components of a sample to see how much of any given substance is in a sample. Put simply, this is done by injecting a foreign substance into the sample to separate every element slowly. It is a very confusing and monotonous process, and I wish I understood it better, but I don't, and I'm explaining it to the best of my abilities. I tried for a while and I couldn't fully understand how it works, but it does a similar thing as the UV spectrophotometer. And the second one that I talked about, high-performance liquid chromatography or liquid chromatography, separates all the materials of a sample at different points through a slow process. Again, a similar purpose as the UV spectrophotometer. They separate through the physical model so that every element is isolated and you can measure how much of something was in the sample. This applies to pesticides because they can isolate the elements or ingredients of pesticides to figure out how many pesticides are in agricultural goods. These are some of the most common physical models when used when assessing pesticides. It's important that we figure out how many pesticides are in our agricultural goods because that helps us assess how healthy our goods are and how safe they are to consume. The final part of my presentation is talking about the physical and chemical process of glyphosate. For a little background, glyphosate is a widely used herbicide that blocks an enzyme for plant growth to eliminate grasses and weeds leaching onto other plants. Again, herbicides are a type of pesticide. It is used extremely commonly worldwide. The molecular formula for glyphosate is 3 carbon, 8 hydrogen, 1 nitrogen, 5 oxygen, and 1 phosphorus. It is a phosphonic acid with a rather simple Lewis structure, as you can see on the slideshow. Like many other pesticides, glyphosate is a serious danger to many. It has been legally labeled an environmental hazard and is corrosive. With constant use, it will not only harm people, but the environment. I apologize, my microphone cut out again, but what I was saying is that it will also harm you and the environment, glyphosate. However, it doesn't necessarily look the part. Glyphosate is an odorless white powdery substance. It could easily be mistaken for many other household chemicals. Glyphosate has a boiling point of 419 Fahrenheit and a melting point of 364 Fahrenheit. It also has a freezing point of negative 20 degrees Fahrenheit. The major issue is that it isn't any less harmful when reduced to other states of matter. Glyphosate is such an innocuous looking material, yet it does so much damage to everyone and everything. What this means is that looks often deceive. We can see that displayed in more than just glyphosate. There are many examples, but just to name a few that look similar to glyphosate: anthrax, strychnine, and white arsenic. It's important to be conscious of what you put in your body, and coming back to pesticides, a lot of the food we eat has been exposed to pesticides, so we must be careful. And for the final part of my presentation, I decided that I needed to eventually talk about my fishbone analysis diagram, so I thought I should just tack it on at the end of this. As you can see, it is about how do pesticides pose a health issue. The first bone of the fish is regulatory. There aren't enough time to test the full effects of pesticides, and little care has been given in the past to make sure that pesticides were safe before they were approved. The second bone of the fish is materials. The materials have been linked to long-term health problems. These include Alzheimer's, cancers, and many reproductive issues. And farmers have a reliance on the large pesticides brands for increasing their productivity and making it difficult for them to stop using those brands, because if they don't, then they will be overtaken by all of the big farming corporations. And on the third bone is types of pesticides. Of the 4 classes of pesticides, pyrethrins or pyrethroids, whatever you'd like to call them, are the lowest in toxicity and usually cause skin irritation. Organophosphates and carbamates damage the nervous system, while organochlorines harm the internal organs and may cause dermatitis. And on the final bone of the fishbone analysis diagram, we're talking about the human level. I took this quote. It says, "A low level of exposure to a very toxic pesticide may be no more dangerous than a high level of exposure to a relatively low toxicity pesticide." And that really does mean a lot. It means a lot because it's more about how often you're subjected to the pesticide rather than the toxicity of the pesticide, because the side effects that you'll face will be because of how much you encounter them. Thank you for listening to my presentation. It might have gone a little bit over, but I thank you for listening to this all the way through.